Okay, what we're going to look at next then is an example of solving an inequality with the radical involved. Okay, and one of the things that's kind of the theme to this idea with using inequalities here is still looking at the bigger picture. All we want to know is really when is this curve, if we were to graph it, when is this curve, in this case, below the x-axis, okay, or equal to the x-axis. Okay, so it's still just a matter of finding the zeros, if you will, because if we can find the zeros for this, then that's going to lead us to a sign chart, and we should be able to find the correct solution set. So I want you to think about, in this case, if we have this times this, okay, this would be of the form a times b equals 0, if you will, if I were to put it in inequality, in equality form. And remember, we use this property every time that we solved a quadratic equation by factoring. Okay, we said that that's a equals 0 or b equals 0. Okay, if a product of two things equals 0, then either the a has to equal 0 or the b has to equal 0. True? So if we were to find the zeros that way with this situation, we could say x minus 2 equals 0, okay, or we could say radical x plus 1 equals 0. And we can find our two zeros in this case because over here we would get x equals 2. If we plugged a 2 into this, that would make the whole thing equal 0. And then bottom line is, what could we plug into this that would make 0? What plus 1 would give me 0? So what plus 1 would give me 0? Wouldn't negative 1 make that sentence true? Okay. And again, you can go through squaring both sides, but if you did, you'd have x plus 1 equals 0. And then you subtract 1 and you get x equals negative 1. Okay? So ultimately, in finding the solutions to this inequality, we're going to do the exact same thing. We're going to make a sign chart with our function. We're going to put our split points, which in this case are both zeros. Okay, we're going to put those onto the number line here. All right. And then there's one important thing that we need to consider here, though, is over here on this side of the negative 1, okay, do I need to actually do a test? And what would happen if I did do a test? Like if I were to take negative 2, for instance, and plug it in. Okay, who can tell me? What problem are we going to run into? Ash? Okay. Yeah, if we were to put a negative 2 in there, wouldn't we get imaginary solutions? Okay. So really, is this stuff over here even part of the domain of this function? No, we can't put anything less than negative 1 in here. The domain of this function would be negative 1 to infinity. So would we even worry about that part right there? No. Okay, that part's not part of the domain. Okay, but if we put something between those two, negative 1 and 2, like 0 for instance, we'd have a negative times a positive, which would be negative. And if we put something bigger than 2, we'd have a positive times a positive, which would be a positive. And so with that said, okay, the question is, when is this less than or equal to 0? Okay, it's going to be less than or equal to 0 between these two. So we would say simply negative 1 to 2. Because again, it's less than or equal to. Okay. If they had asked us for greater than, we would have said from 2 to infinity. Questions on that one? All right. One other type that I want to look at then next. This is actually on page 262 in your book if you want to follow with me. This time we have a rational function, okay, but it also has an inequality, or not an inequality, but part of the inequality is having an absolute value. Right? So still we're going to perform that same analysis. We want to find the points that are going to be our split points, which are going to be, number 1, our zeros, and number 2, anything that will make this undefined. So once we do that, then we can make our sign chart. Okay. The zeros here, the top would equal 0 if we plugged in a 2. So x equals 2 would be a split point. And then here, in the absolute value, we would have a negative 3 would make this 0. So x equals negative 3 would be another split point. And again, nothing much changes here other than that we have to pay attention to the absolute value part when we do our test. Okay, so if we were to put in a negative 4, the top would be negative. And no matter what we put in, the bottom is always going to be what? It's always going to be positive. So we'd have a negative over a positive, which would give us a negative. And if we were to put in a 0, let's say, we would have a negative over a positive, which would give us a negative again. And then anything bigger than 2 is going to make the top positive. With the bottom always being positive, we would have positive there. Now, when we write the solution set here, we have to be a little bit careful here, because if we have a less than or equal to, okay, normally we would say from negative infinity all the way to 2. Okay? But what's the problem with negative 3? Negative 3 wasn't a 0, it was what makes the function undefined. True? So can we include negative 3 in the solution set then? No, because negative 3 is an asymptote. So when we write the solution here, we have to say negative infinity to negative 3, okay, and then from negative 3 to 2. Okay. And again, it said greater than or less than or equal to, so how about the 2? Remember, the 2 is a 0, so if the 2 makes it equal 0, then we would go ahead and include that too. The key issue here, though, is that we got to make sure we don't include the negative 3, because the negative 3 is an asymptote. So if we went from negative infinity to 2, okay, we would have included that asymptote, which we cannot do. The asymptote is not part of that function. Okay. Questions on that one?